Hello everybody, welcome back to another Gregorious Maths video. Today I'm going to be continuing my abstract algebra series by cutting off group theory short and starting ring theory. Okay, I might reintroduce some group theory a lot later on in the series in the context of Galois theory and field theory or whatever. But right now I'm going to be introducing rings and some basic definitions and generalizations. So let's get straight into it. A ring is kind of like a more specific group, but the main difference is that it has two operations. Okay? So remember that a group G has one operation, normally denoted multiplicatively, but a ring has two operations. So a ring are equipped with two binary operations, multiplication and addition, is a ring if. Now number one is that it's an abelian group under addition. Now I'm not going to make you go back to my very old video on abstract algebra to check what that is. I'm just going to tell you the axioms for a group, okay? An abelian group, more specifically. So, there exists a zero in R, okay? Such that A plus 0 equals A for all A in R. So number one is the addition of the existence of an identity element. So there is this zero element such that it doesn't make a difference whether or not you add it to A, for some A in R. Okay? Okay. Now number two is the existence of negative A in R for all A in R, such that A plus negative A is equal to 0. So we have inverses. So for some A, we have an additive inverse negative A, such that they will cancel out. Basically, they'll make the additive identity. Okay? Now number three is that it's associative. So A plus the quantity B plus C is equal to A plus B plus the quantity C. And these are the axioms for a group under addition, but for it to be an abelian group, it must satisfy number 4, which is that for all A and B, for all A, B, C in the ring. Okay? Now, for all A, B in the ring, A plus B equals B plus A. Okay, so it's commutative. It doesn't matter which way around you do the addition. Now, these are the axioms for an abelian group under addition. For it to be a ring, A, it must have two operations, multiplication and addition. It must satisfy these conditions under addition, and now it must satisfy these for multiplication. Number 5. 1, it has the distributive property. A times B plus C is equal to A times B plus A times C. Number 6 is that it's commutative. So A times B is equal to B times A. And of course this is for all A, B, C in the ring. Okay. And number 7 is that number 7 is that it's associative. It's associative. Sorry, that took me a little while. So A times B, and then that quantity times C is equal to A times the quantity B times C. Okay, this is what a ring is, the bare minimum, okay? However, we can generalize further with a ring with unity. A ring with unity is a ring R such that, okay, there exists a 1 element in R such that A times 1 equals A for all A in the ring. So now a ring with unity is a ring that not only has additive identities, but it has multiplicative identities too. But no, we're not done generalizing here, because we have an integral domain. Sorry. You know, I'm a teen, I have mood swings. I can chuck my pen. Anyway, an integral domain is a ring R, is a commutative ring with unity Oh, sorry, this is not actually required for it to be a ring. This is required for it to be a ring, a commutative ring. Implies commutative ring. Sorry. Oh, actually I want to put an exclamation mark because that might look like factorial. Okay, I'll just underline it. Okay? So, an integral domain is a commutative ring with unity such that we have cancellation. So, for all A, B, and C in the ring, C times A equaling C times B implies that B equals A. And now we have the definition of a field, which is a further generalization of these rings. Okay? A field... Sorry, I won't write it in blue because that might look like the same definition. I'll write it in pink. I like pink. I have butterfingers. Anyway, a field K, let's call it, is a ring R such that for all A minus 0 in the ring, we have it that there exists a inverse such that A times A inverse is equal to 1. Now we are done generalizing these rings for now. Tomorrow we're going to look at sub-rings and etc. But for now, these are the definitions I'd like you to know. Now, a quick thing to note is that a field implies cancellation. Why? Well, if C times A equals C times B, and we know that there are inverses, then we can multiply both sides by C inverse, which would cancel out the C's on both sides. However, an integral domain does not imply a field. For example, the integers are a good example. If we have 2 times x equals 2 times y, for all x and y in the integers, that does imply that x equals y. However, the only elements in the integers with inverses are 1 and negative 1. So, now, we're going to look at a quick little theorem about these rings, and then we'll be done. Oh, no. So I was about to do the edit, but anyway. And then we'll be done. The first theorem I'm going to prove is that A times the 0 element, so the additive identity in the ring, is equal to 0. Now, how to prove this is to make use of the distributive property. And this is my own proof, okay? So, this implies that A times 0 plus 0 equals 0. Actually, hold on, we're just going to say A plus 0 times 0 equals A times 0. Now, because of the distributive property, this implies that A times 0 plus A times 0 is equal to A times 0. And now, because of the existence of inverses, we can subtract A times 0 from both sides, meaning that A times 0 is indeed 0. Okay, now we're going to prove another thing about including negatives. So, if A times negative B, if we have A plus times negative B plus A times B, this equals A times negative B plus B, which equals, those two are inverses, so these two cancel out, which equals A times 0, which equals 0 from here. So A times negative B must be the additive inverse of AB. So A times negative B is equal to negative AB. Now, using this, we can prove it the other way round. So if we have negative AB, this is equal to negative AB plus 0, which is equal to negative AB plus, now we have AB minus times, plus A times minus B, which is equal to, by the associativity of addition, is equal to negative AB plus AB plus A times negative B, which is equal to A times negative B. So those two are equal. Okay? And now what would happen if the ring with unity, if we say that 1 does equal 0, if 1 equals 0, that implies that A equals A times 1 is equal to A times 0 is equal to 0, hence R is equal to 0. Hence the whole ring is equal to 0. Okay? And these are just a few little facts about rings and a couple of examples of proofs using the properties for rings, which I came up with myself. And hopefully they're all correct and etc. etc. Yeah. I'll see you in the next video where we cover homomorphisms, ideals, and subrings. Goodbye.